Eating, salutations, all those nice things. Welcome to topic 4. This is antidifferentiation and integrals. Huge focus of the course thus far has been on differentiating, finding derivatives, instant rates of change. And in this topic, we are specifically looking at going the other way. So in this introduction to antidifferentiation, we're going to take differentiation and then oppose it. So going the other way. Hopefully, in theory, at this point, you've already taken yourself through these first couple of pages. That was, in theory, what I instructed. But who knows? And on those pages, you might have gotten some results. You can compare to this. These might be some guesses you have. Who knows? On the second page, I want to focus some attention here. We've got these 4 big F's of x, and we found the derivative of each of them. We found the derivative of each of them. And in each of those cases, we notice f prime is the exact same thing, all 4 cases. Why does that happen? Well, we know the derivative of x squared is 2x, and that's common in all of these. We know the derivative of x is 1, and that's also common in all. But the derivative of -5, +4, -19, +24, even though those values are all different, they're all constants. And the derivative of a constant we know is 0. So if we were told that f prime was 2x plus 1, we couldn't necessarily say exactly what f of x could be, because there's some constant that could be added at the end, and we don't know what that is. When we anti-differentiate, when we find what gave us a certain derivative, essentially, we do have to account for that constant being there. And the way to do that is just to straight up add a plus c. So we know if we take the derivative of x cubed, we get 3x squared. So if we take the integral, as this is called, of 3x squared with respect to x, we get x cubed plus c. We don't need to state c is some real number. That's kind of assumed in the context. You just need to have that plus c to say, yep, totally accounted for it. There's something else there. Now, our process for anti-differentiating is called integration. Integration is kind of based on adding together a whole bunch of tiny areas, which we'll get into a later lesson. But because we're adding together tiny areas, we have this symbol that kind of looks like an S. Whatever we have to take the antiderivative of, whatever we are integrating, is going to be between that weird S thing and the dx, right? That with respect to x part. So in the middle is what we're deriving. And it's with respect to whatever variable is stated at the end. And that's kind of that. There are some examples. If we take an example like this, we're taking the integral of 2x with respect to x. When I attempt this, I'm going to first just look at the variable. I've got x with a power of 1. What did I derive to get x to the power of 1? It must have been x squared. Then I double check the coefficient. This coefficient is currently 1. By the power rule for taking derivatives, the new coefficient will be 2 times that 1, which gives us the 2 that we're after. So this is super duper pooper scooper. It's a-okay. The only thing we need to do is say, but, there could be some constant there. Maybe it's 0, maybe it's 75. I don't know. But that one is done. Take a moment, try the others just for funsies. See what you get. Pause the video, all that jazz. Resume after a few minutes of trying. All right, well, you paused the video and you restarted. So here we are. I'm tackling this one. The first term, 6x squared, that must have come from taking the derivative of x cubed to get that one higher exponent. And then by the power rule, I took this 3, multiplied it by whatever coefficient was there to get this coefficient of 6. Therefore, whoopsie daisy, that coefficient must have been 2. And I can always back check this, right? What's d dx of 2x cubed? That does get me 6x squared, so we're all good. The next one has an x, as we see. That must have come from x squared. What's its coefficient? Well, 2 times whatever this coefficient is needs to get us a 1. So that coefficient must be 1 over 2. And then finally, this last term has x to the 0, so it must have come from x to the 1. And if we take its exponent, multiply it by this coefficient, we have to get this 2. Therefore, its coefficient must be 2. This is pretty much done. We are missing one piece. But as we go through this process, we're kind of talking it out, trying to really pick apart what's that coefficient supposed to be. As you go through this more and more, you're going to find that coming a bit more quickly, that essentially division process getting put in there. But it's always a good idea to just double check what happens if we take the derivative of this. Do we actually get this result back? Anyways, this was missing one piece. We do absolutely need to put that plus c at the end, then that's done. I'm going to just kind of plop out the other ones here. Oh, no, I'm not going to plop them out. I'm going to do something here. One thing worth noting for differentiating, or anti-differentiating for integrating, is that whenever we have a constant multiple of something, we can yoink that out. It's the same as if when we were taking, say, the derivative of 8x squared. We could pretend we're taking 8 times x squared, look at just the derivative of that x squared, and multiply it by the 8. That's kind of where the power rule came from. But similarly, if we're looking at this particular integral, we can say that's kind of like taking the integral of 1 over x with respect to x and multiplying it by 2. We don't have to take that step, but it is a good thing for us to recognize. Just in terms of where this idea leads and things we can do with integrals later on. And then when we see that, we might more directly see, well, this thing that we're taking the integral of, the integrand, if you will, that comes from ln of x. It does not come from x to the 0. That's a constant, so it's not that. But it does come from ln of x. And since we've got this 2 in front, we essentially just have 2 of ln x. And that's that one, dun, done. But again, you want to double check your answer, differentiate, go the other direction, make sure it's okay. Same as if you want to check your answer from division, multiply, see if it works out. Cos x is the derivative of, speeding along too fast, I missed something in the last example. Hopefully you didn't also miss it. Plus c. Yikes, that was close. All right, cos x is the derivative of sine x. 4x is the derivative of 2x squared. And of course, not forgetting that plus c that gets added in there. And then finally there's like 4,000 more. Okay, second last example. We can use that same property of, hey, this is a constant multiple, plop it outside. So we can say this is 4 times the integral of 5 to the x ln 5 dx. We can't yoink out this 5 to the x and plop it outside because that's not a constant. It's got an x in it. We could do it with the ln 5. We could take that and plop it outside because ln of 5 is a constant value. There's no variable involved in it. But the reason I would leave it like that is because I recognize this, and hopefully we all recognize this, as the form of a derivative. It is the derivative of an exponential expression. More specifically, 5 to the x ln 5 is the derivative of 5 to the x. And since we're multiplying that integral by 4, we say we're taking 4 times that expression. And then, of course, we add the constant at the end. Last one. You can take it in steps if you want, if that makes it a bit easier. We're taking the integral of x to the 1/2 dx with respect to x. So, exponent-wise, that must have come from x to the 3/2. What did we multiply 3/2 by to get a coefficient of 1? It must have been, 2/3. And then, as always, plus c. Any questions, comments, concerns? Just kidding, I can't see you. If I could, that would be weird. And I like to think I'm not weird, but who knows? Anyhow, all these examples, we added that little plus c because any constant value there would allow that to still give us this same derivative as what that integrand is. There are ways we can find c, but it does require us to have more information given. Like this. Here, we know f prime is 2x plus 3, but we also know f of 2 equals 6. And that's enough information to put this whole, I just erased something. Yep, a c. And that's enough information for us to find f of x in its entirety, like what that actual constant value is. For starters, we can say that f of x must be, I can do a way better symbol. That looks good. The integral of f prime of x dx. You don't really have to write that step if you don't want to, but it can help just kind of frame your thoughts. So we're taking the integral of 2x plus 3 dx. Good form, we should probably put that in brackets, although in theory it's implied. And then evaluating or simplifying that integral. The 2x came from x squared, and the 3 came from 3x. And there is, of course, a constant. So that's one part of this. The other part is saying, hey, we know what f of 2 is. So if f of x is x squared plus 3x plus c, we know that f of 2, which is, oh my gosh, let's put this in pink. Since f of 2 is equal to 6, we can say that 6 is equal to 2 squared plus 3 times 2 plus c. So taking this line that we knew f of x to be equal to and just subbing in everything we knew. F of 2 is 6, and that happens when we plug in 2's for all the x's. You can solve that in 1,000 steps, you can solve it in 1 step, but at some point you need to verify that c must be -4 in this case. How did I get that? Well, there's a 6 on this side, there's a 6 on this side. They cancel each other out. Move 2 squared to the other side at the end. Take a moment, try the next one. See what you get. Usual, pause the video, and then resume after you've given it a shot. Oh, and you paused, and you're back. All right, G prime is stuff. Leash. Okay. And the graph of y equals g of x has an x-intercept. Okay. I'll figure what that means later. I have no idea what an x-intercept is. It's weird words. I'm going to say that g of x is the integral of g prime of x with respect to x. So, g of x is the integral of 3. I might write this x with a 1/2, like as a power of 1/2, just to, again, help kind of frame my thoughts, give me a sense for that power law that will apply. And we'll have 3/2 for that. 3/2 times something gives us 3, so that must be 2 as a coefficient. And then minus half x squared plus c. The graph of g of x, the graph of y equals g of x, has an x-intercept at x equals 9. And that means when x is 9, g of x must be 0, right? The y value has to be 0 at an x-intercept. So we can plug that value in. Since g of 9 is 0, we can say that 0 is equal to all that stuff we had, but when x is 9. That's about that. I might take this in multiple steps. I mean, you could do it in fewer, but yikes. 9 to the 3/2 is 27. 2 times that is 54. And then we're subtracting 4.5. I mean, you could keep it as a fraction if you want, but I don't want. And again, if you want to write that as a fraction, sure, go for it. But since it was a nice, easy terminating decimal, I'd just keep it as a decimal. You do have to use a fraction if you can't express it as a terminating decimal, so just keep that in mind. Anyways, practice work. I suggest trying it, see how it goes, and that's my whole story. Okay, bye. Ugh, they changed Desmos, and now, or not Desmos, Notability, and now I just have to go back to record it to stop recording. Honestly, it's just ridiculous. Stop this.